Hi and welcome back. In this particular lecture, I'm going to talk about doing how to perform residual analysis once we've built our regression model. So in the previous lectures, we've covered a fair amount of topics important in while building regression models. So we talked about in the previous lecture, we talked about overfitting and how overfitting can actually bias our model towards explaining only the variance in the training data, so much so that it starts to explain the error term, and the performance on validation or the overall sample starts to deteriorate, and how we can look at R square and adjusted R square. Now, going back to the assumptions of OLS regression, one of the assumptions of OLS regression is that the uh, the residuals or the error term that remains in the model, the difference between y and y hat, the error term should be a normal distribution with a mean of 0, and it should be IID. So how do we actually generate the residuals automatically in SAS? So while once we build the model and we get the parameter estimates, we can manually multiply the parameter estimates with the columns and generate the y hat. There are procedures and options in SAS which can do this automatically for us. More specifically, if I use the output out statement, I can specify a new dataset which will be created, and I give the option p equal to predicted, so it will create a new column called predicted, which will have the values of y hat, and r equal to resid, so it will create a new column called residuals or resid, which will contain the difference between the actual value of the dependent variable and the predicted value. So y minus y hat is automatically stored in this variable. Then we have certain other options also, which is L95 and U95. So this is nothing but the lower 95 confidence limit for the predicted value and the upper 95. So in the previous regression lectures, we had covered regarding the standard error of the regression. And using the standard error, we can always do predicted plus minus the 1.96 standard errors. So that will give us the upper and lower 95 confidence intervals around the predicted mean. So I'm going to try and show you how to generate residuals automatically, and then we will do some kind of residual analysis on this. For this particular example, we want to look at the telecom data set. So I have the telecom data set already imported in SAS format, and let's have a look at this data set and the dictionary. So we have information regarding the customers of a telecom service provider, and we have a lot of variables regarding the measurement of these customers. So we have the region of the customer, the tenure, how long the customer has been with the organization or been a customer. We have age of the customer, marital status, address, income, education, and so on. And then we have what type of service the customer has been enrolled in, and so on. We have a lot of variables over here. And what we can do is we're going to build a model, and let's build a model with which age is a continuous variable, so we'll make that as a dependent variable. So age is a function of all the other variables in this particular model except for churn is a variable which specifies whether the customer left the company or not. So we leave churn out, and using all the other variables, let's build a model, and let's try to predict age as a function of the variable. So we will apply all the techniques that we've covered to date in this particular modeling exercise. We will look at the collinearity in amongst the variables. We look at the significance amongst the variables, and we'll use certain automatic procedures, backward, forward, or stepwise, whichever is appropriate, and generate a final model. And then post that, I want to look at the residuals. So first of all, I'm going to get this data set. It's already in SAS, and let's start off with the modeling procedure. Now there are a lot of variables. I want to copy them automatically, so I'm going to use the proc contents procedure to get a list of variables. I'm going to do proc contents data equal to data dot telecom, and I'm going to run this, and let's have ODS HTML. So this is the proc contents procedure, and I have the variables already in my uh, in a table, so I'll just copy them, and let's bring them into an Excel sheet. So I could have just copied it from the data dictionary, but to make sure that there's no spelling mistakes, etc. while importing into SAS. We'll let it be. And I'm going to ensure that the variables that I put into my model are the correct variables. So I don't want to put in a variable which is nominal and use it like a number in the data set. So proc reg data equal to data.telecom model age equal to, and I'm going to use, so address is a variable in the data set which is a nominal variable, so it's coded as numbers and it should not be used directly. So we should convert this into the binary variables using one hot encoding. But for this example, I'm a little lazy, so I'm going to let it be. But if you want, while you're following this exercise on your own computer, you can actually change it into a binary variable and create multiple columns. So a region has got, I believe it's got 3 regions, region 1, 2, 3. So you need to create at least 2 variables to capture this nominal variable. So let's look at the other variables. So marital status is a binary variable, so I can directly use it. So model age equal to tenure. I can't use age at in the list again. Marital income. Education again is a nominal variable, so let's leave it out for now. And all of these variables are fine. Then we've got a list of binary variables. This is also fine. We've got some log transform variables, which is also fine. Customer category again is a nominal variable, so we can't use it. So the correct method would obviously be to convert these one. So I've got one nominal variable here. I've got 2 nominal variables. I've got 3 nominal variables, and each of them have got 4 to 5 categories, 3 to 4, 5 categories. So we would ideally want to convert them into the one hot encoded binary variables. But I'm going to skip that procedure for now, and in the interest of time, I'm going to skip it. But I would suggest that you, in your SAS code, while you're writing, create these variables separately. So you might end up with a better model than I do. I'm going to let this be, and I want to look at the VIF as well and start pushing out variables which are highly collinear, and that looks all about right. So this is my initial variable, and let's say profiling VIF over here. So I'm skipping one big step over here, which is I am skipping outlier analysis and checking if any variable has got an outlier. And we need to go do that variable by variable, but for this particular exercise we'll skip that. And let's look, is there an error? No, there's no error here. And let's open the model up. Yes, there's a model out, and we've used, okay, so there are a lot of missing values in our data set. So what's happened is for variables with missing values, it has automatically excluded those rows. So SAS is automatically excluded. So if I look at the data set over here, I observe that log transformations have a lot of missing values, and this is a problem because log of 0 will create a problem. So I'm going to actually remove these 4 variables from my data set, modeling 1, 2, 3, 4. So I'm going to remove log toll to log wire from the data set. So here is log toll to log wire, and let's run this again. So unless I replace the missing observations with 0, SAS will not use them. And let's look at how many observations were used in this modeling procedure. All models, so all observations used. So this is a good table to actually check whether you've committed an error or not. And let's look at the p-value. So the regression is coming up as significant, and that's good news because that means at least one of our independent variables has got a significant relationship with the dependent variable, and we can proceed now. And let's have a look. Root mean square error of 7, dependent mean of 41. So average age is 41. The average error is 7.27. Coefficient of variation is 17%. R square is 67. Adjusted R square is 66. It doesn't look like too much overfitting, but we'll see the variable p-values. And here we have the parameter estimates, And my god, so looking at the variance inflation factor, I see a lot of collinearity available over here. So we've got 13, so let's keep a VIF cutoff of 10. So I've got 13 over here, and I've got 16, 160, so this is the largest. For now, is there anything higher than 116? No. So it's going to be a painful procedure, but we need to remove collinear variables one at a time. So I need to check out long mon from the data set. So let's remove long mon. So where is this particular variable over here? What are the, so wireless and toll mon. So between wireless and toll mon. So here we go. So I'm going to remove long mon. And I'm actually not going to copy paste the code again and again. So we're going to use the same code procedure here. And let's open the data set, sorry, the output. Let's look at the fit statistics. So as soon as I've removed longmon, I see that the VIFs have dropped for the other variables as well. If we are lucky, we don't need to remove anymore, but we're not that lucky. So next up seems to be equipmon. Is there any other variable which is higher than that? So that's 32. Let's check that out. Equipmon. So between toolmon and here, so there it is. Off with equipmon. These variables are completely functions of other variables, so they are pretty much useless in bringing in new variants to the table. So we can do without these variables. Let's look at the latest fit statistics. Anything else? So the VIFs for other variables continues to fall. There we have cardmon at 11. Anything else? Yep, wiremon is still at 20, so that is the higher one. So I see the VIF of other variables started to fall. Maybe wiremon is the last variable I need to check out to put everybody less than 10. So let's go and pull the plug on wiremon variable. Except where is it? Wire 10, tall 10, long there. Wiremon is there. Let's remove that. Let's execute this again. Let's look at the latest fit statistics. Is there anything else which has got greater than 10? So I have a few more. So card 10 is at 12 right now, and cardmon is also at 11. So I need to remove card 10. Let's go and pull the plug on card 10 for now. So cardmon, there it is, card 10. Let's remove these. So typically variables which are direct function of others will get caught out in the collinearity trap. So a lot of these variables are actually log transformations of each other, and they'll start to get weeded out. Let's have a look again. It looks like we've solved the collinearity problem for now, and we've got a we've got a pool of eligible variables now. So the highest VIF that I can see is 5.7. Is there anything else? 6.96 for Tolmon, and that's it. So this is our set of variables with which we can start to work after solving the collinearity problem. Now I see that we have a lot of p-values which are insignificant, or variables which don't have a significant relationship with our end product. And as you can see, after removing so many of collinear variables, our R square and adjusted R square have not changed that much. So we are the regression model as such has not suffered too much. And removing these insignificant variables, so we have a string of variables with high p-values, and they all need to go. And I'm a little lazy, I don't want to do it manually, so I'm going to use the selection procedure itself. So I'm going to just say selection equal to stepwise, and we'll do SLS equal to 0.05, SLE, so SL stay and SL entry both at 0.05, and let's run it with this. And have a look at our result now. and we will have a huge number of steps. So this is the stepwise procedure which we covered in our previous lecture. So each one by one the variables are entering into the model, and let's scroll down directly to uh, the stepwise summary selection. So it's run a full forward selection model. So these variables have entered the model one by one, and the total R square that we've managed to achieve is again 66719. And let's look at the final model that we are getting. So this is the final model that we've generated. So these are the final variables that are coming in, and we look at the p-values. All of them are significant. So I just think there's one error with it's still running. So let me just cancel this. Yeah, so this is a problem with my SAS. So it didn't execute the procedure completely. So these are the variables that finally enter my model. So what I will do is I will copy these variables out and rerun the PROC REG procedure only with these variables. So I don't need to run the selection procedure again. So let's copy that out, keep it here, and I'm going to run the procedure again over here, and I'm going to say final model based on stepwise selection. Final model based on stepwise selection after removing collinear variables. So I'll just copy the starting procedure from there, from the above procedure. So we have proc reg data model and age equal to over here. So let's give this, and the variables that do enter the model are only these variables, and that's it. And this is my final model, and I'll just save it, and let's execute and have a look. Yeah. So I look at it, the R square is 0.6719, adjusted R square is 6683. They're very close to each other. There's no divergence. I look at the p-values, and the p-values are all significant and all are less than 0.05. And this is my automatic model, the final model, with which I'm capturing 67% of the variance in my dependent variable. And I've already ensured that all my independent variables are independent of each other, i.e. there is no collinearity. And if you look at the estimates, you can see employment has a positive estimate, i.e. as employment years of employment increase, year increases by about 0.43. So every year in increase in employment gives a 0.43 years in increase in the age. Same with the address. Every year lived in the same address increases the age. These all make sense. And you can see that retirement has a huge impact. Retirement is a binary variable, so a average retired person will have a positive impact of almost 15 years as compared to 0. That's a huge impact. Reside, it seems, has a negative estimate, i.e. number of years residing at the same location. You're likely to have the age goes down, and this could possibly be because you've not yet moved out of the parents' home. So that's another reason. Marital again has a positive impact, a positive slope. If you're married, and marital is a binary variable, so if you're married, age goes up by 2.69 as compared to getting multiplied by 0. And then we have the estimates against the type of program that you or the type of SIM card or the subscription they've taken with the company. Gender has a negative estimate, but we don't know 0 or 1. So let's check what does 0 and 1 in gender actually imply. 0 means male, 1 means female, and 1 gets multiplied by -1. So females are younger than males in this data set. And then cardamom and call weight. So these are our, this is our final model. And I want to do residual analysis on this. And I want to generate the residual data set automatically, rather than what I can possibly do is I can copy this into an Excel sheet and then do multiplication and generate the predicted value manually or using an Excel formula. I can implement it in SAS as well, writing some code. But in SAS we have this option, output out equal to dataset, and I'm going to use this option in the PROC REG procedure to automatically generate the dataset. So what we need to do is, in the same PROC REG procedure, after the final variable has been entered, we give output out, and we give, let's say, the dataset where you need to store it. So I'm going to say telecom underscore age predicted. So I'll just say age p equal to predicted, r equal to residual. I want the lower 95 and upper 95 estimate of the age as well. Instead of a point estimate, we are going to give a 95% confidence interval estimate regarding the mean age of the customer. So that gives us a range with which we can guess, and the assumption is that guess will be correct 95% of the time. And let's run this procedure once more, and let's run this. Yeah, and let me just close this step completely. Yeah, so let's check the log. Okay, 1,000 observations, 46 variables were generated. Let's look at, so I've saved this in the work dataset because I did not give a day in this. I did not give a library name over here. So let's look at the telecom underscore age underscore predicted. So I see this dataset has got the for all the original variables which were there in the dataset used for modeling, and then we have the predicted value of age. So this is the predicted value of age. Name is predicted, so I gave the option p equal to predicted. So if I want the variable name to age predicted or something, I have to change it over here. I can write age underscore pred, etc., whatever I want. P is the reserved keyword over there. Similarly, R is the reserved keyword. So if I want the residual column name to be residual, I can write full residual over here. So I've just given resid. So we've got the predicted value of age. So this is the label, and the actual name is predicted. Then we have the lower confidence interval and the upper confidence interval. So that is using the multiple the standard error of the regression, and the standard error, as we can see, 7.23, and that's the root mean squared error term. And when we do 95% confidence interval, we are actually multiplying with the close to 1.96, or about 2 times, so about 14 times plus minus the actual value. So 40 plus 14 gives me 54, and 40 minus 14 gives me almost 26. So each of these predicted values are then changed into upper and lower confidence intervals by adding and subtracting the number of approximately 14 from it. So we get the 95% confidence interval regarding the age of the customer. And then we have the residual. And this is the variable which I'm interested in. And this is the difference between y hat, which is the predicted value, and the actual age value. So which is over here. So this is age, and this is the predicted value of age. If I actually generate a PROC plot and plot age into predicted, this will give me a scatter diagram between y and y hat, and I should hope that it is extremely correlated. Let's have a look at this, and there you can see we have a correlation over here, and then you can see that over here we get a tight variance, and then over here we get slightly loose variance. So a little bit of heteroscedasticity might be there, and we'll check that out a little later. And this looks good to me. And if I want to generate the PROC core between them, so what is the correlation that you would expect over here? I forgot to give the data option. It picked up the data from the previous uh, procedure. That's something new for SAS for everybody. So var age and predicted, and I get a correlation of 0.81. And if I square this correlation, what would be the value? So the square of this correlation would actually be the R square of my model, and I remember the R square is 67%. So there we have it. So the square of the correlation between the actual and predicted is also the R square of the model also, and that's holding true. And now I want to look at the residuals, and what are the properties of the residual in a linear regression. We know that the mean residual is 0 and it is normally distributed. So let's do a proc means on this. Proc means data equal to telecom, and I want to do a var on the residual and run. And there we see the mean of uh, the variable is 1.59, and with sorry minus 1.59 raised to power 10 into 10 raised to power minus 14. So this is 0.0000 all the way till 14 zeros and then 159. So effectively the mean is coming out to be 0. The standard deviation is, or the average deviation is 7.19, which will be very close to the 7.19 figure should be very close to the root mean square error in our model as well. So if I look at the root mean square error in the model, so that's about 7.23. So root mean square error and the standard deviation in the residual will be very close to each other because the formulas are almost the same. Only thing is root mean square error is divided by a smaller number, which is divided by n minus 1 because of the degrees of freedom. We are using the degrees of freedom over here, and in standard deviation we are using n minus 1 observations directly. So we are dividing the total variance by 999 to get 7.19, but for 7.23 we are actually dividing it by 988. So that's why root mean square error is slightly larger, but both of them can be interpreted in the same way. And I also know that the residuals should follow a normal distribution around the mean. So I'm going to do a normality check on the residuals. Normality check on residuals. So how do I do a normality check? I'll use the PROC univariate procedure and generate a histogram of residuals. So we all know what a normal distribution looks like. So I'm going to use the histogram, and we've covered this in our previous, in fact, one of our first few lectures itself, how to generate a histogram in SAS. So it's going to be var resid and then histogram resid, and I'm going to give an option slash normal over here. So what this will do is will run a few hypothesis tests checking the normality of the variable. I'll do an ODS HTML and let's run this, and there we get the univariate procedure result. So the mean of the variable is 0, standard deviation 7.19, and now this is very interesting. So this is doing a it's doing a single sample t-test with the h-naught that the underlying population is also 0. And I look at the t-value of the t-test, since the mean is the sample mean is also coming to be 0, we are essentially doing 0 minus 0 divided by the standard deviation, so the t-value is also 0, and we get a p-value of 1. So in case you get a mean which is slightly off from 0, you don't need to hesitate. If the standard error is big enough, your sample mean would not be significantly different from 0. And let's look at our histogram. So this is what the histogram looks like. We've got a slight a spike on the left hand side where we would not expect it, but overall it seems to follow a normal distribution. But is this an actual normal distribution? Are we 95% sure? Can we do a hypothesis test on this? So let's look at what the hypothesis tests are saying. And what we see over here is some goodness of fit tests for normal distribution. The null hypothesis being that it is a normal distribution, alternative being that it is not a normal distribution. And what we can see is the p-values are low. In fact, if my p-value is alpha at 1% and 1%, only in that case it looks like a normal distribution. If I'm checking it at alpha at 5%, p-value is low, null has to go. So this is not normally distributed, and that seems to be a violation. What can we do about it? Probably not much. It would probably mean that I can start playing around with the variable, start adding and removing if that's a problem I want to solve. And it seems to be that one or two observations which are creating some problem over here. So it could be that outliers are there in my data set. So while the mean is 0, it does not seem to be normally distributed. So there's some deviation from a normal distribution over here. So while the p-values are low, they're not so low, and with a little push, they might actually go above the alpha of 5%. But for now, it doesn't look like. So that's one test this model is failing. And one more thing that I can do is I can check, I can generate a ggplot between, or a scatter diagram between the age variable and the residual variable, and that should not also have any kind of trend ideally. So let's look at this. I'm going to plot age into the residual. Since the residual is the random error, there should not be any trend over here, but let's see. So we have, this is the previous G plot, this is the, and here we have it. So this looks like the scatter diagram between age and residual. As you can see, let's plot it the other way around so it becomes easier to interpret. So I'm going to do residual into age. So force age onto the x-axis. Yeah, and there you can see the problem is that our model is not homoscedastic. Is not homoscedastic. As you can see, the residuals around smaller ages are smaller, but as the age increases, the residuals become much larger, and that's where the underlying problem is coming in. Our model is not able to generate the same kind of performance it shows in the smaller age ranges. Beyond age of 40 or 45, you can see that the variance suddenly explodes. So this is an interesting. I'm just going to copy this out and let's see if we can paste it over here. Yeah. So this is an interesting concept because what's happening is, can I draw on this? So let me just paste it onto MS Paint. Yeah. So as you can see that in this area or this point of in this range of age, the uh, the variance that we can observe in our data set, or variance that we can observe between actual value age and the error that we are getting is tight and it's constant. From this point onwards, actually the variance is starting to increase dramatically, and that's a problem for us because residuals are supposed to be IID, i.e. I can take the residuals from this range and compare it with the residuals from this range, and they should have the same mean and standard deviation. So over here, while the mean may be the same, positive residuals and negative residuals are cancelling out each other, so that mean residual is still 0 over here, but the standard deviation is much larger. Here the standard deviation is much smaller around the mean, here the standard deviation around the mean is much larger, and that could be a property of our underlying data as well. So it's not something which can be easily fixed, and it may just so happen that it's very difficult to predict the age of older people correctly using our data. So looking at this, our data is able to predict between ages, let's say late teens to maybe 40 45 pretty well. Even there we can see the trend is still to have larger variance as the age increases. So we do have a problem in our data set that as age increases, our variance in the error is also increasing, and that may or may not be easily solvable. And that could be, this is a violation. However, does that mean we junk our model? Not necessarily. And does that also mean that this model cannot be applied onto business? Well, it all depends. It's okay to have errors, and if we know that the errors in the larger age groups are going to be large, as long as we know that, there's no reason why we can't still go ahead and use the model. What it essentially tells me is that lower 95 and upper 95 for the larger age predictions are not going to be very accurate. So they may be okay for lower age predictions, but for larger age predictions, the lower and 95 and upper 95 are going to be larger because the standard error is certainly underestimated in these cases. The standard error is much higher over here than over here. So lower 95 and upper 95 estimates will not be accurate in the higher age ranges. That being said, the model performs fairly well up to age 50 or so, and we are still able to capture a large part of our variance in the model. So all in all, while the model may make business sense to go ahead and apply, it is not necessarily that we should strive always for a statistically stable model. Sometimes in real life that's just not possible, and we need to learn to live with it. So this was an example where we did residual analysis for the telecom dataset. What I would ask you to do is revisit this particular dataset. and try to include these variables as well. So we've got a variable which we have not included, which is region and education. And let's see whether education is actually significant or not. So if I want to check for education, I'll just do an ANOVA on this. So let's do PROC ANOVA data equal to dataset name, which is data.telecom. And if I remember the procedure for the syntax for ANOVA, so let's look up the syntax for ANOVA. Here we have, so class variable, model test variable equal to the class variable. So the class in this variable is education, which is ed. So is it ed? Sorry, let's look over here. Yep, so it's ed. So let's go with that. Ed model age equal to ed. So I'm assuming that education might have a significant impact on age. And let's look at the result. And our procedure data class levels. So we should have 4 class levels. Yeah, sorry, 5 class levels. So what are the class levels that we have? Did not do high school, some college, and a postgraduate degree in college. So that's good. The p-value is low, null has to go. Therefore, a level of education has an impact on age, and a very strong impact also. And what we can do is what in our next steps, and I'll leave this so I won't build a video for that. Why don't we bring in region as a indicator, as an independent variable, education as an independent variable, and customer category also as an independent variable by using one hot encoding, redoing this, checking for collinearity, running stepwise on this so that we end up with only the significant variables, and then redoing the residual analysis and see whether we can beat. So in our previous model, we got 67% of the variance explained, but we got hung up on the residual analysis over here. So redo this and check whether the residuals are coming out to be normally distributed with a constant variance across the age parameter. So while I don't expect it will have too much of an impact, but I would like ask you to do this on your own as well, and check whether in fact it helps or not. So this was our exercise on linear regression, and more specifically on how to do residual analysis, how to generate a histogram, how to check for normality, how to check for the mean value of the variables. And before I end this lecture on multiple linear regression, I just wanted to show a brief regression checklist that we do when we are building a regression model. So we can follow a step-by-step procedure in actually building a regression model. The first step that we need to do, and while we in these examples we didn't do because we're working with datasets we already know, is that we need to check for distributions of all the the dependent and all the independent variables. What it essentially means is check the range and check the box and whiskers plot for both of them. For dependent variable, independent variables, identify if there are any outliers in any of these. If there are outliers, you may want to exclude them from regression analysis because we are calculating variances every time, and variances are extremely susceptible to presence of outliers. So just like correlation can change a correlation of 0 to a high correlation due to presence of a single outlier, regression is also very closely related to correlation. So we don't want any outliers. So remove outliers. So outliers can either be removed or capped. So capping is when if we have an outlier, we simply recode this to a lower value. So for example, a rule of thumb is that the observations should not be plus minus mu plus minus 3 sigma, where mu is your sample mean x bar and plus minus 3 sigma, where is your sample standard deviation. So any value which is greater than 3 sigma from the mean is brought down to 3 sigma. Any value which is lower than mu minus 3 sigma or x bar minus 3 sigma is brought up to x minus 3 sigma. So we do capping. So that is capping. So either you can delete the observation or you can cap the observation at these extreme values. So again, the removing or capping outlier, anything above or below 3 sigma, 3 standard deviations can be removed or capped. If we are building a predictive model, you could divide the data into training and validation. So I'm going to cover this step in our next few lectures on logistic regression and predictive modeling in more detail. So in case it's not a predictive model, you can skip this step. If you're building a predictive model, you may want to divide the data randomly into training and testing, build the model on training and check the R square on testing again. Once you've done that, check for multi-collinearity using the correlation matrix or VIF, remove all collinear variables. After that, reuse variable selection, either automatic or manual. Remove all variables which have p-values greater than alpha. Once you've done that, check goodness of fit parameters, check the ANOVA of the regression, R square and adjusted R square. The difference between R square and adjusted R square should not be too large. So check for overfitting. There should be no overfitting in our model. And overfitting can happen when you have a large pool of eligible variables, and it's very easy to get caught in the trap of overfitting. Look at the standard error and coefficient of variation. So R square is not the only parameter for checking the goodness of fit. Also check for the standard error and coefficient of variation. Then do the residual analysis. Look at the max error term in our regression. What is the maximum error that we are getting? In some cases, the maximum error might actually be an unacceptable error. So you might have, so always you will have always a mean error of 0, and you may have a high R square as well. But if your max error is larger than the tolerance acceptable in real life, that model might actually be discarded. So use the residuals and check what should be your maximum error, whether the residuals are normally distributed mean of 0 and whether they're homoscedastic or heteroscedastic. After that, once you finalize the model on the testing data, you can use the model to score the validation data and recreate the same analysis again. So check for R square. You can do the R square simply as the square of the correlation in the validation predicted data and the actual value of the dependent variable and square it. Check for the standard error again on the residuals, and you can do the same residual analysis test on the validation data as well and see whether all the checks which were holding true in training, are they holding true in validation as well. And if everything is fine and everything compares up well, you have your model and you're ready to go. And that was the regression checklist that you must look at while doing a regression modeling exercise. And we've covered all of these steps in parts over the last few videos that we've been through. And this was the first major topic that we've covered after we've built up our basics using hypothesis testing. In the next few videos, we'll start talking about predictive modeling using logistic regression. And logistic regression is again an extension of linear regression itself. And that's why it's very important that we understand all the basic concepts of linear regression very clearly, because all the assumptions that we've used in linear regression will be used and we will build upon them when we do logistic regression. So I'll see you in the next video.